I don't normally give talks with sunglasses on, but these are really awesome. Thank you. Someone else has put theirs on as well. They're for sale downstairs, so I thought I'd wear them. So my name's Dr. Jen Gupta. I work at the University of Portsmouth, down on the south coast of England, in a department called the Institute of Cosmology and Gravitation, which basically means that I work in a department that does astronomy and cosmology, studying the universe. And so today I want to talk to you about the invisible universe. But before we get onto the invisible universe, we have to talk about the visible universe. So what do we see when we go out at night and we look up? Well, we'll see something a little bit like this. So we've got some lights on in here, so you might not be able to see this really well, but hopefully you can see there's a few dots of light on there. These are our stars. If you go out at the right time of the month, you'll see the moon. If you go out at the right time of the year, throughout the year, you can see different planets in the sky as their positions change compared to our position around the sun. But this is the kind of view that you'll get from a town or a city. You see some stars, but not loads. So this actually shows the constellation of Orion here, with the 3 stars, 1, 2, 3, that make up his belt there in the middle of the constellation. And this is a photograph taken from Cardiff, and it illustrates why we don't see lots of stars, because you can just about make out a sort of orangey glow. See the cloud there is a little bit reddy orange. This orangey glow along the horizon is light pollution. So this is all the lights from the houses and the cars and the street lights and everything like that. This just makes the sky too bright. It lights up the sky and means that we can't see the fainter stars. So to really do astronomy, to do stargazing, we have to go somewhere really dark. And when we go somewhere really dark, we see something a bit more like this. So suddenly we see a lot more stars. This was taken from the South Downs, just outside of Brighton. And you see so many stars from a dark site that sometimes it's quite hard to pick out those familiar stars, those constellations, the star patterns like Orion. It can be a bit confusing, but Orion is still in this picture. Here's 1, 2, 3, the stars making up his belt there. And in a way, this picture shows you the invisible universe, because this shows you stars that are invisible to us from a town or a city. These fainter stars we can't see from a town or city because it's too light. But that would be a bit of a cop-out if I was going to stand here for 20 minutes and talk to you about light pollution. So what else do we do? Well, for thousands of years, for as long as people have been people, really, we've been astronomers. We've done astronomy. We've looked up at the sky just with our eyes, and we've observed the stars and planets and the moon and tried to make sense of it all. So this is something like you might see. Here's the moon down here, and these 2 bright dots here are actually 2 of the planets, Venus and Jupiter. And as I said, for thousands of years, people looked up with their eyes, but 400 years ago, just over 400 years ago, in 1609, an astronomer called Galileo was one of the first people to take all the optics knowledge that had been known for hundreds of years before. A lot of it developed in the East. Took that knowledge of optics and of lenses and of how light works and put it together to make a telescope. So Galileo here was one of the first astronomers to do that, putting 2 lenses in a tube and pointing that up at the sky to magnify the view that they saw. And this is what Galileo saw. So this is a photograph. This obviously isn't exactly what he saw. This is a photograph showing what he would have seen when he pointed his telescope up at Jupiter. You see a big disk here, that's your planet Jupiter. And he noticed what looked like stars on either side. And up here, actually, this is drawings of what he did see. It's actually from his publication. So what he saw was the planet, this big circle here, and stars on either side. But as he observed from night to night, he saw that the positions of those stars changed. One night he observed it, there was 1 on the left and 2 on the right. A few nights later, there's 2 on the left and 2 on the right. And so he realized that these aren't stars. These must be moons going around Jupiter. And this was one of the big pieces of evidence at the time to back up this idea that was emerging that the Earth wasn't the center of everything. That instead the Earth was one of the planets that orbit around the sun. Because if Jupiter has things going around it, has these moons going around it, then not everything can go around the Earth. We have better telescopes now. These are the kind of images that you can take just using a telescope you can buy in a shop. You start to see colour on Jupiter. You start to see detail on the cloud surface. And you really start to get some fantastic images. I mean, that will take a lot of effort to get an image like that, but it can be done with amateur telescopes. And of course, then we get to the professional telescopes, and the best telescope of all that we have to do optical astronomy, visible astronomy, is the Hubble Space Telescope, which has taken these images. And then we see incredible detail on Jupiter, and we also start to see detail on the moons going around it. Telescopes have allowed us to see things that we can't see with our eyes. Telescopes allowed us to discover the last two planets in our solar system. Uranus and Neptune are too faint for us to see with our eyes. They're too far away from the sun, but telescopes can see them. We see star formation regions, galaxies like that look like we think the Milky Way looks like, galaxies that look like car crashes, stunning images that we get from our space telescope. And I think that astronomy, cosmology, astrophysics, whatever this science is, whatever name you want to give to this science that I do, it's simultaneously one of the most accessible and inaccessible sciences at the same time. It's really accessible because anyone can be an astronomer. You all can be astronomers if you aren't already. All you need to do is wait for a clear night. You might be waiting a while in the UK. But the next clear night that you have, you can go out, you can look at the stars, you can look for the moon if it's the right time of the month, you can look for the planets. You can go out night after night and see how that changes, and you can start to piece together the science that drives everything you see in the sky. So it's incredibly accessible. You don't need anything beyond your eyes to do astronomy. But it's also incredibly inaccessible because we can never go there. We can't go to this galaxy and take a close-up look. We can't go and grab bits of those distant stars and bring them back and test them in the lab to see what they're made of, to see what temperature they are. Everything that we do in astronomy and astrophysics and cosmology, we do because we look. We do it by looking at the light that comes from these objects, or sometimes the light that doesn't come from these objects, to work out what's going on. And so we have to manipulate light. We can't just rely on what we see. And one thing we do is take advantage of this. So hopefully some of you will be familiar with images like this. If you're a prog rock fan, this is the cover of Dark Side of the Moon. If you're a scientist, this is what happens when you shine white light through a glass prism. The white light is actually made up of all the different colours of the rainbow, and as it travels through the prism and out again, it gets spread out into its components. And so if you do that with white light, you get all the colours of the rainbow. But you can get other lights. You can make light by heating up a gas. Different elements of the periodic table, things like hydrogen, the most abundant element in our universe, the first element in the periodic table. If you put electricity through a gas of hydrogen and make it glow, it will glow pink. And if you put that pink light through a prism, instead of the full rainbow, you just get this. So you get a red colour, you get a turquoise colour, and you get to purple. And this is the spectrum of hydrogen. Hydrogen gas only gives off certain colours of the rainbow. And other elements in the periodic table, every element in the periodic table, has its own unique spectrum. So if you look at these different ones that I've just shown here for examples, they all look different. And so if you see this pattern that I showed you before, you know you're looking at hydrogen if you shine that light through a prism. If you see this one, you know it's helium. So the same gas that you get in your balloons that makes them float. If you take that helium gas, put electricity through it to make it glow, and then pass that light through a prism, that's what you see. Sodium, the old orange street lights, that light is actually made up of these colours. Oxygen that we breathe, neon that you get in your neon signs. If it's true neon, it's a combination of those colours. And so this is great for astronomers because now we can actually work out what stars and galaxies are made of. We can take the spectrum, the light from those stars, we can put through prisms, we split it up into its components, and depending on what pattern we see, we identify what's in those stars. And one of the first people to do this was this lady, Margaret Huggins, along with her husband, William. They basically devoted their lives to astronomy. Their house in London was an observatory, which sounds fantastic. And what they did was they took the light through their telescope, they pointed their telescope up at stars, collected the light from that, passed it through a prism and onto photographic plates. And they took the spectra of stars. So obviously this is black and white, but every one of these lines is where a line of colour would have been. And so this is the spectrum of the sun, identifying the elements in that. This is the spectrum of another star for comparison. And they really paved the way for astronomers today. Today we use telescopes like this one. This is the Sloan telescope in New Mexico. The mirror, which is down here, which is the width of this, is 2.5 meters. That's 2.5 meters across. And instead of taking photos of the spectra these days, we turn it into graphs, which are shown here. So imagine this is your color going across, and this is how bright it is. So every time there's a spike, that's where you would have seen a color. And Sloan's taken like 3 million spectra today. So 3 million stars and galaxies out there, this telescope has taken the spectrum of. So we've managed to understand a lot more about what the stars and the galaxies are made of. If you see what they're made of, depending on what elements you see, that tells you about the processes going on in those stars and those galaxies. But that's still just visible light. Even though the spectra, this rainbow, is invisible to us, no one, I hope, is seeing rainbows right now when you look at these lights. It's still just the visible light. But this visible light, this rainbow, is actually just a small component of light. It's just the part that our eyes can see. And the entire thing is what we call the electromagnetic spectrum. So beyond the red part of a rainbow, or those rainbows that you see when light goes through raindrops, the exact same effect. It doesn't stop at red. There's light that's redder than red, and that's called infrared. On the other side, there's light that's more violet than violet, and that's called ultraviolet. And then it keeps going. So on the red side, it goes to infrared, then microwaves, then radios. On the violet side, it goes to ultraviolet, then X-rays and gamma rays. And so you might not be familiar with thinking of these types of radiation as light, but hopefully you are familiar with some, if not all, of those. Because we use our radio waves for communication. Your mobile phone uses radio waves. Your satellite TV will pick up radio waves being beamed down from satellites in space. Microwave light is used in your microwave oven to heat up your food. Infrared light is used for thermal imaging. Humans give off infrared light. So the army use it for night vision. If you've ever seen any of those police TV shows when they're in their helicopter at night trying to find the criminals down on Earth that are running away from them, they'll have a thermal camera, an infrared camera trained down on them to spot them. Ultraviolet is the harmful radiation that comes from the sun. The reason that we put sun cream on is to protect us from the UV rays from the sun. Of course, some people go and sit in sunbeds and get blasted by UV light to create that effect of a tan. X-rays are used in medical imaging. And I couldn't think of an everyday use of gamma rays, but if you are familiar with the Marvel universe, then the Hulk became the Hulk because Bruce Banner got exposed to a lot of gamma rays. Now, I'm not saying that can happen in real life. You'd probably just die, so no one go out and douse yourself in gamma rays in the hope of becoming a superhero. But I couldn't think of an everyday reason. So what I'm going to do now is go through our electromagnetic spectrum very quickly and show you an example of how we use this in astronomy. So I've picked objects that could hopefully be seen with an amateur telescope. You might have to be pretty good at amateur astronomy to pick it up in your telescope. And I'm going to show you what they look like at these other types of light. Now, bear in mind, I've only picked one example for every part of the spectrum, and of course you can see lots of different types of objects at these different spectrums. So I could probably just pick one object and show you all the view. Anyway, we'll start with radio. So for radio, I've picked this object. This is a galaxy called M87. We're looking at this fuzzy blob here in the middle. And so M87 is a galaxy. It's a collection of 100,000 million stars, all held together by gravity. And it's an elliptical galaxy, so you can think of its 3D shape like a rugby ball. That's all it is, a rugby ball shape of stars. And so it just looks like a blob on the sky. It doesn't look very interesting. This is the picture taken by an amateur astronomer. So if you want to try your luck, and this is very hard to do, here's a really bad screenshot from Stellarium that you can't really see. It's down there. So I put some stars. This is the constellation of Leo. So to find Leo, look for the backwards question mark, forming the head of our lion. And then go down to his tail. And that kind of points you towards M87. If you actually want to find this object, download an app or go online to look for it. That's what we all do. So we pointed the Hubble Space Telescope at this galaxy before. Astronomers have done that, and this is what you see. So this is now just 1/4 of that blob of stars. And you already see it's a little bit weird. Here's the middle of the galaxy, and there's something coming out from the center. And you don't see that in most elliptical galaxies, so we already know that's a little bit weird. If we go to radio, that's much stranger. So this is now an intensity false colour map. Obviously, we can't see radio waves. So what we've done here is made it red, where the most radio waves are coming from, where it's brightest in the radio. And then it goes down to yellow, and then green, and then blue as the background. And you see the same thing coming from the centre. It's going off at a different angle there just because the picture's rotated round. But that thing coming out there is exactly the same as this thing coming out here. And so what's happening in M87 is that it's one of these active galaxies, one of the kind of galaxies that I studied for my PhD. What's happening here is that in the centre of every galaxy, there's a supermassive black hole. It might be 1 million or 1 billion times the mass of our sun. And in most galaxies like the Milky Way, it's not doing anything. But in M87, it's a monster. So it's actively eating up everything around it. You've got your black hole in the middle, you've got all this stuff swirling around, and it's all falling into the black hole. And somehow that makes this jet form. There's actually one going off the other side as well, but we don't know how. What we do think is happening is that the magnetic fields have all got stretched out into a line going up like this. You've got magnetic fields coming out from the top and the bottom of the system. And then you've got electrons, the negative part of the atom. And when you have electrons and a magnetic field, what it does is it spirals round. So you've got electrons spiraling round this. And as that happens, if you've got electrons going around a magnetic field, they give off radio waves, something called synchrotron radiation. So that's what we think is going on there. That picture was taken with this telescope. This is the Very Large Array. So most telescopes are like mirrors. So you can imagine your radio waves coming down here, hitting this dish, and they all get bounced, reflected up to this bit here, that's the receiver. So they come in and go up there. But this looks like lots of radio telescopes. And that's because to make a good radio telescope that's got a good resolution, that can see a lot of detail, it needs to be really big. To have a radio telescope with the same resolution, being able to pick out the same detail as the Hubble Space Telescope, it needs to be the width of England. So instead of us being all here in a building, instead of you all having your houses around here, we just have a massive radio dish. And I don't think that's practical. So instead we build smaller ones, we point them all up at the same part of the sky. And it's as if you had a radio telescope that stretched from there all the way to here, you just haven't had to build that one structure. Okay, microwave. Microwave is very similar to radio to astronomers, but there's one thing in particular that we look at in the microwave, and that's the entire sky. So this is an all-sky photograph taken by an amateur astronomer. What this guy Nick has basically done is gone all around the world and taken photos looking directly up. So if you imagine you go everywhere around the world, take a photo looking directly up, and you put them all together, you've essentially taken photos of the inside of a ball that surrounds the Earth. That makes sense? And so just like with the globe of the Earth, you can unfold that to a 2D map of the world. You can take that inside of that globe surrounding the Earth, that inside globe of the sky, and unfold it to a 2D map. That's what this is. So we see our galaxy here. This is us looking through our Milky Way. In the microwave, this is what it looks like. So here, white is the brightest, and then it goes to blue, and then red and yellow. All of this stuff here, the white and the blue and the lilac, that's all stuff from our Milky Way. But what we're really interested in here are the speckles at the bottom and the top. So people did a lot of work to subtract our galaxy, and in fact all other galaxies from this picture, and what you're left with is this. So this speckly map of the entire sky is showing you the oldest light in the universe. This is what we call the cosmic microwave background radiation. It was emitted 380,000 years after the Big Bang. So this light has been travelling across the universe for nearly 13.5 billion years. We pick it up with our telescopes today, and what it essentially shows you is a temperature map. And the average temperature of this radiation is 3 degrees Celsius above absolute zero. It's really, really cold. But the red parts are where it's 1/millionth of a degree hotter, 1/millionth of a degree. And the blue parts are where it's 1/millionth of a degree colder. So overall, it's very uniform. Those are tiny, tiny temperature changes. And that's a piece of evidence that the Big Bang is the right theory about how the universe began. But these little changes give us hints of why the universe looks the way it does today. That was taken using a satellite called Planck. Here's an artist's impression of it. It has to be an artist's impression because this telescope was 4 times further away from the Earth than the Moon. So it's really far away, and we can't send astronauts there to take a photograph. But it orbits. Here's the sun, here's the Earth, and here's Planck. So it orbits around the sun behind the Earth, which means that it can stay really cold and it can pick up that really cold radiation. Okay, infrared. Infrared, I'll go back to our picture of Orion. And so if you can find Orion's belt from a dark site, coming straight down is what's called his sword. And if you're somewhere really dark, one of those stars won't look like a star. It will look a little bit fuzzy. With a telescope, you might be able to see something like this, and you realise that it's what we call a star formation region, a nebula. Zooming in on that with the Hubble Space Telescope, we see something like this. So you mostly see dust. You see a few stars, in particular there's 4 stars here that you can just about make out. But you can't see the stars that are forming inside because the dust hides the view. Infrared light gets through that dust, so then suddenly, in our infrared picture, we see maybe 300 stars. Some of these are what are called brown dwarf stars, stars that are kind of failed stars, and some of them will be the young stars that are forming. Both of these pictures were taken with this telescope. Now, this is a photograph. This is a photograph taken by an astronaut of the Hubble Space Telescope, because that telescope is in low Earth orbit, and the space shuttles could go there to fix it. So Hubble has optical cameras. It has cameras that's sensitive to the light we see, but it's also got infrared and ultraviolet cameras on it as well. We'll skip out visible and go up to the ultraviolet. Ultraviolet, I've picked this object. Can you see that sort of fuzzy blob there? A lot of astronomy is fuzzy blobs. If you go somewhere really dark, you might see something like that if you look in the right place. So that's over there. Here's Cassiopeia, one of the most famous constellations. Use these 3 stars to find the area of sky that you're looking for. Look in that part of the sky, somewhere really dark, out the corner of your eye, you might just see that little smudge of light and it will look rubbish. But with a telescope, with our professional telescopes, this was taken with that Sloan telescope I showed you earlier, we see that M31, this object, is actually another galaxy. So this is a spiral galaxy, like we think our Milky Way looks like. And so in the middle here, you've got the bulge of kind of yellow and orange stars. And coming out around it, you've got the spiral arms. They look very dark in this picture. Probably darker because I've got sunglasses on. But all of this dark stuff is dust, and that's where the stars are forming. If you go to the ultraviolet, it looks really different. So here now, the centre isn't very obvious at all. And that's because those stars are mostly red. So they're not giving off any radiation from the violet part of the rainbow or the ultraviolet beyond that. But we really see now that spiral structure. And this is where all the young stars have formed. And when stars form, they're very, very hot. And they're so hot that they glow in the violet and the blue and the ultraviolet parts of the spectrum. Over there. That was taken with another space telescope. This is a Swift telescope that's an ultraviolet and also an X-ray telescope. Again, an artist's impression. Move up to X-ray. And for X-ray, I've picked one of the most recognisable pictures, I think, from the Hubble Space Telescope. But from this, you probably won't get what it is. It's another fuzzy blob. This is the Crab Nebula. So if you want to find this object, it's there. So here's Orion's belt. It's sort of up from Orion's belt. But hopefully some of you have seen this picture before. This is kind of the picture that's on coffee table books, like around the world. And what the Crab Nebula is, what you're seeing here, is a supernova remnant. So this is what's left over when a star much bigger than the sun explodes at the end of its life. Stars much bigger than the sun explode as supernovas. That gas in the outer layers is flung out, and that's what we're picking up here. All of this is the outer parts of that star that's been chucked out. But the center of the star, the core of the star, collapses down. If the star is really massive, you end up with a black hole in the middle. But if it's slightly less massive, you get what's called a neutron star, a star made up of the neutral part of the atom, condensed down really, 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 really dense. And some of them spin, and then they're called what are called pulsars, because they spin and they give out 2 beams of radio waves and X-rays. They're a bit like cosmic lighthouses. So imagine I'm the neutron star, and these are my beams, and I'm spinning around, and they're going like 30 times a second or more than that. And we can see that in the X-ray, and I think this is incredible. So here is the X-ray picture, and here's our pulsar in the middle. You can see the 2 jets coming out. And these pulsars are incredible incredibly accurate timekeepers. So they spin really fast and they spin really accurately. So in fact, you can time better using a pulsar than using an atomic clock. That's how regular they are. Okay, final one. Oh, sorry, that was the X-ray telescope. So this is Chandra. You have to put your X-ray telescopes in space because X-rays don't get through the atmosphere, which is really good. Otherwise, we'd be fried with X-rays right now. But it does mean we have to put our telescopes up into space. And finally, gamma ray. Now, gamma ray, I don't have any really impressive pictures to show you because gamma ray astronomy is fairly new. It's pretty difficult to make a telescope to pick up gamma rays because they're so energetic. Gamma rays can't be focused to a point. You know, I said about the radio waves bounce down and focused up to a point. All of the other telescopes work like that, but gamma rays can't be focused. So all I can show you is the entire sky again. So here's the optical part, and here's the gamma ray. So yellow is the most gamma rays, down to red, then blue, then black. You see a lot coming through the middle. That's all the gamma rays coming from our Milky Way. It's not that the Milky Way gives off that much gamma ray emission for a galaxy, it's just that we're inside it. So all these things that are giving off gamma rays are much closer to us, so they seem really bright. But what I'm really interested in this picture is all the stuff outside. You see all these little dots of gamma ray emission above and below. Those are all other galaxies. So those are all stuff outside of our Milky Way. And nearly every single one of those will be one of those active galaxies. Cast your mind back to radio, where we had the M87, that elliptical galaxy with the jets coming out from it. Nearly all of these dots are also galaxies like M87. And so we've got these galaxies that are really bright at radio on one side of the spectrum and really bright at gamma ray on the other. And so why is that? Why is it that they're so bright at the extremes? That's one of the things we're trying to figure out. That was taken with this telescope, again an artist's impression. As I said, they work a little bit differently. So you've got this box, it works a bit like the detectors at CERN at particle accelerators. Your gamma ray hits here and it can change into a pair of particle and antiparticle. And then that can go down and change into other particles, and it basically creates like a shower of particles through this material that ends up at a detector layer there, which measures the energy of the particles, it measures the direction that shower came from, and then it works backwards to figure out where that gamma ray came from on the sky. So that's our spectrum. Very quickly, if you like looking at the multi-wavelength invisible sky, check out a website called Chromoscope that some of my friends have made. They've put the all-sky images at the different wavelengths, at the different parts of the spectrum up. And so you can scroll through it. That's the infrared, down to microwave and radio, and you can zoom in and have a play around. So that's chromoscope.net. If you want to help us out with our science, at Portsmouth we're part of what's called the Zooniverse, which is a collection of citizen science projects that basically gets people like you to help us with our research. So this is one called Milky Way Project, milkywayproject.org, and this shows you infrared pictures of our galaxy and asks you to mark out like bubbles, or if you can see any star clusters, and basically that helps the scientists to do their research. Or you can do Radio Galaxy Zoo, which is at radio.galaxyzoo.org, where you're shown an infrared picture, that's what the colour is, and a radio picture, that's what the lines are, and it asks you if they match up to each other to try and find these radio galaxies like M87. So I will finish there. If you want to get in touch with me, that's my Twitter, that's my website. If you want to find out more about my work, that's its Twitter, that's our website. We're on Facebook as well. I've got some postcards as well if anyone wants to come up and get one at the end. And I'm happy to take any questions. Thank you.
Have you got any questions for Jen?
Yeah, what is cosmic dust? You mentioned dust.
Dust.
I presume it's not a dust.
No, it's one of my friends is a professor who works on dust, and she keeps on trying to convince me that cosmic dust is really interesting. So it's stuff like, it's very fine stuff like silicas and things like that. I don't know too much about cosmic dust, if I'm completely honest, but apparently it's very interesting. So because what dust does is it absorbs light in and then it re-emits it at other wavelengths. So I think it actually like steals about half of the light from stars and galaxies and stuff actually gets sort of absorbed by dust. That's about as far as I can tell you. Any other questions?
Why to beam from the pulsars?
Why two beams? I'm not quite sure. You see that quite a lot, two beams coming out from the poles at different, so pulsars have it, the active galaxies have them, stars when they form sometimes have two things, not quite sure. I guess it's to do with the active galaxies, it's probably to do with how everything's rotating and it sort of Why was it up and out of the two ends? But it's not sure. Yeah.
How do you know that is Galileo's actual piece of work? Because for all we know, government or other people could have just put it there and said, this belongs to Galileo, this was a piece of work, we have it. For all we know, that it could have been lost underground somewhere.
So I mean, that was really important work, so it's been kept hold of people. So what happens was, like, you know, those publications got written and then they end up in the libraries of like the Royal Astronomical Society and places like that. And there are people who work on like verifying if work is genuinely you know, that person's, but you know, it would have been in like the library at Oxford or something. You know, a copy of that would have been sent to the different universities at the time, and then they've been kept there for a time. Good question. Yeah.
What research in cosmology is going on at the moment?
What research in cosmology is going on at the moment? Everything. So one of the big things that cosmologists are trying to figure out is what's dark matter and what's dark energy. So everything, all these atoms, everything that makes all of us up and everything around us, or the ordinary matter, is only 4% of the universe. So then there's dark matter, which we think works like how ordinary matter works. So it has gravity, but it doesn't interact with light, and that would make up about 20% of the universe, 25. And then the rest is dark energy, which we really have no idea about, but is making the expansion of the universe accelerate. So those are two of the big things that we're working on in Portsmouth. I've got colleagues who are trying to prove Einstein wrong, so working on modifying theories of gravity. So I don't know how much you know about gravity, but gravity started with Newton and the apple falling on his head, the classic story, and he worked out how gravity works on Earth. But then Newton's gravity doesn't really work in the solar system, particularly Mercury's orbit caused a problem for Newton's gravity. And then Einstein came along and modified that, came up with relativity. And so Einstein's modifications of Newton's gravity work really well in our solar system. But on the biggest scales, it doesn't quite work again. I've got people who are trying to do that, which is always a bit funny. It makes a laugh. I'll take one more question and then I think we're probably going to have to move on.
Yeah, one more. Please.
Yeah.
What is the black moon?
A black moon? So are you meaning black hole? Or black moon? Black moon is not really a term. Pardon?
It's in the news. It's coming out tonight. The black moon.
There's not a term that's used in astronomy. It might be that we're at a new moon. I'm looking to Sue at the back. Yeah. No.
It's more visible tonight. They're saying it's more visible.
Don't know, to be honest. I can certainly have a quick look. And
It's when you have 2 new moons in a calendar month.
Yeah.
So it's the second new moon.
so that's the blue moon. So blue moon.
But it's called the black moon.
Yeah, so that's the similar concept of blue moon. But it's
Okay. Oh, right, okay. Here you go. You taught me something. Good. That's a great thing.
Because the Islamic calendar changes.
Yeah.
And it comes every year, but it's at a certain time in.
Yeah. And so I had a colleague actually who was trying to see if you could use, tried to see if you could use radio telescopes to really accurately determine when the new moon exactly starts for the Islamic calendar.
Yeah.
No, one thing for the children in the audience, scientists don't know everything. So I love it when I get a question that I don't know the answer to. Cool. I think we better stop, but if people have got questions, I can answer them outside while we switch over.
Thank you, sticking with the space theme next, we've got Sue talking about the Rosetta satellite mission.
mission.
Was it? Do you call them a satellite?
just landed on a comet.